So in the last class we learnt about K maps, 2 variable and 3 variable K map. So we are going to expand that philosophy to solve 4 variable Boolean expressions also. Now if you see in 4 variable, now the thing is this is 0 0 0 0, this is 0 0 1 0 1 1 and then 1 0, right? We wrote 1 1 and 1 0 here in the 3 variable K map because while moving from here to here there has to be only one change, from here to here there has to be one change. So this was like an 0 0 0 1 1 1 and then 1 0. And the same thing we need to now there are 4 variables w, x, y, z. So here also it is going to be 0 0 0 1, right, and then we write the 4 and then 1 1 and then 1 0 here, right? So you will find the min terms accordingly now going to be changed like this. Okay, 0 0 0 1 1 1 and 1 0, and even in the y axis it is going to be 0 0 0 1 1 1 and 1 0. Okay, so this is just the expansion of the fundamentals which we saw for 2 and 3 variables. Now if I see the min terms m0 m1 m2 m3, okay, m4 m5, then m6 in the last and then m7, then we are going to skip this entire row, come here m8 m9 m10 m11 m12 m13, then go to the last m14 and m15. Okay, so these are the positions of the various min terms in a 4 variable K map. Okay, so you see now initially we saw only gray code being applied here. Here the gray code is there in both the axes. Okay, m0 m1 m2 is going towards the rightmost and then m3, m4 m5, m6 is in the rightmost and then m7. Then you are leaving one row, coming bottom here because it is 1 1, so it is 1 0 here. So m8 m9 m10 m11 m12 m13 m14 towards the right and m15. Okay, so these are the position of the various min terms in a 4 variable K map. Okay, now if you see from here to here also, these 4 corner cells also, obviously all the adjacent cells there will be only one variation. If I see these 2 also, you will see this is 0 0 1 0, this is 1 0 1 0, so only the MSB is changing. So here also you will find only a 1 bit variation in the top cell and the bottom cell, and from here to here also if you go these corner cells, you will find there is only a 1 bit variation, 0 0 1 0 0 all zeros. Okay, 1 bit variation. So let's take some examples. Now it is 1 3 4 5 6 7 11 14. These are the min terms. Let's map them. So this is an m0 m1, so m1 I have put 1, m2 is m2 is 0 here in the corner, so m3 is here. Okay, now m4 m5 m6 is in this corner and m7, so so this m6 here and then m7 here, and then this is right, in fact I should have done the animation separate, then you will find m8 9 10 11, so this is 11, right, and then 12 13 14 15, so you will find this. So now I can make an 4 box here. Now this is going to be an 4 box here, one combination. Now what do the expression which I write here? Now this is an 3 variable K map. So if I make an box of 4, I will have 2 variables. Now if you see here, both w and x are varying as we keep moving from top to bottom. W is changing from 0 to 1 and x is also changing. Only thing which is not changing is y and z. So the expression corresponding to this 4 box will be yz. Okay, similarly I can make one 4 box out here. Okay, now if you see here, as we are moving towards in the horizontal direction, y and z is changing, whereas w and x is not changing, but w is 0 and x is 1, so I write it as w dash and x. Okay, now there are 2 which are remaining here, right? Now you have to see what is the biggest possible square possible with this one, and obviously you can't combine these 2 out here, but for these 2, what is the biggest? It is not 2. You can make an 4 box out here, right? So I am going to make an 4 box here, right? Always I have to see what is the biggest possible square which I can make. Now for these 4s I can write it as this becomes xy. Okay, this is gone down here. It is xy, right? Because if you see here, between these two, x is common, w is changing from 0 to 1, and here z is changing, y is remaining. So this is xy. Okay, let me correct it now itself. Where was that? Okay. Yeah. Yeah, so this is xy. Now this one is remaining here. Again, I make a big 4 box. Instead of making an 2 box, I make a big 4 box. Now if you see here, between these 4 boxes, now w is 0 here, x is changing, so I have w dash, and between here z is now y is changing, z is remaining constant, so w dash z. So the final expression will be this, right? You have 1, 2, 3, 4 boxes are there, so corresponding to that 4 expressions is there. So this is the simplified way we can implement this function. Okay, now you require 1, 2, 3, 4 4 2 input AND gates and 1 4 input OR gate. Okay, is this thing clear? What we require for hardware implementation is 4 2 input AND gates and 1 4 input OR gate. Okay, so this is how we take one more example out here. So you have an 0. 0 is 1, so I put 0 here. 1 is 0 is not there. 2 comes here. 3 comes here. Then 4 is 0. 5 comes here. 6 is not there. 6 is not here. 7 comes here, right? And then I go after that. It is 8 here. 9 here. 10 here. 11 here. Okay, this animation is also 10 here and then 11 here. Okay, and then I got 12 is not there, 13 is there, and right. Okay, now so once having put all the ones, now we need to make the boxes. Now here if you see, these 4 elements in the corners can be grouped as one 4 element box. Okay, this thing is also possible. Okay, all the 4. Now if you see what is not changing in these 4, if you see here in these 4, y is changing 0 and y, so that is ruled out. So z is not changing. Here z is 0, here also z is 0, so z dash. And if you see here, this is 0 0 and this is 1 0, that means x is also not changing 0. So this 4 is nothing but x dash plus z dash. Okay, now so these 4 ones have been taken care of. Now you can make one more 4, this 4. Okay, this is clearly yz. Okay, because all these w and x is changing, y and z, so I can straight away write that yz. Okay, now that is done. Now another 3 are left out here, so I can make one box here. Now I can't make a 3 element box. Okay, that I told you will have to go either with 1 box, 2 box, 4 box, 8 box, like that. I can't make a 3 element box, because if you try to make 3 element box also, you will not get an expression. Okay, simplified expression. So I go for a 4 element box out here. So if you see, the expression for that will be xz, because if you see here, x is 1 for both this, and like this, and z is 1 for both these columns, so xz. And now this 1 remains. Now here again I told you can make an 2 element box like this, and which is not optimized, so you have to think, if possible we have to go for a 4. So there are 2 ways you can make 4. Either we can make this 4 like this, or we can make an 4 like this horizontal. So both the options are available. Okay, so if I make a box like this, then this will become a yz. If you see why it is yz, because z is 1 here in both this, and in these things in this blue you will find w is 1 here, so it becomes wz. Okay, so this is wx and yz, so w is 1 out here. So this light blue turns out to be yz, so I can write an expression. Okay, there is instead of this last light blue, you can have this the entire bottom row also. You can club it. Okay, that will give you yx dash. Okay, instead of yz, I write yx dash also. That is also perfectly fine. Okay, essentially they will give the same number of gates. Okay, that way, as long as the box size remains same, you can take that also, doesn't matter. So there's 2 possible solutions in this particular problem, right? Okay. I think that, okay, this is another problem out here. Is it the same? Yeah, another way of grouping out here is, okay, you have these ones and these ones. Again, you can make it a 4 box. Initially we took these 4, right? So instead of that, these 2 and these 2 also can be taken. So if you see these 2 and what is this here, y is remaining constant and x is 0 for these the red ones. So you have x bar and a y, and then you have you can make this also a 1 box. Okay, that comes out to be x z. So 1 is remaining out here. So again you can make this box, or you can again here also you have an so you can make so 2-3 combinations is possible. So you have to see to it that you should not land up making more number of small boxes. As long as the number of big boxes remains same, the answers will be correct. Only thing is the way the variables are arranged will be slightly changed. Okay, so here I guess there is one more possibility, yeah, that we discussed. There is one more possibility of having these 4 also together. So these are all the different possible combinations which are available when we are using K maps for simplification of 4 variable maps. Okay. Yeah, this is showing one more possible combinations. They are all the same. Essentially, now you have to try and make boxes which can accommodate the maximum number of ones. Okay, if possible here, there could be a possibility of having 8 element box also. Suppose it is 1 here, it is not so in this case. Suppose it is 1 here, so I make this entire thing as now 1 box. Okay, in that case what will be the expression? Here you will find y and z are changing, right? Okay, here, okay, so no, if I make this entire thing, okay, 8 box here in this, I can make like this. If I make an entire big box with 8 variables, then you will find w and x is changing because you are cutting across all the rows. Column wise y is also changing. Then if I make an 8 box, then it will be merely z. The value will be merely z. Okay, is it clear? Let me give you one more example. Suppose it is all ones in the last 2 columns. Okay, last 2 columns, if you are going to make an box with 8 of them, then it will be 0 0 0 1 1 1 1 0. So all x, y and x is changing, so we discard that. Then if you see, between these 2 columns, okay, z is changing. So if you make a column of a box of 8 variables between encompassing all these 8 ones, then it will be, that expression will be just y. Okay, similarly, if I make an horizontal, like first 2 rows, if I make one 8 box, okay, then it will be like y and z are changing across different columns, whereas x is also changing. That will become y bar. Okay. Please listen carefully. If the first 2 rows everything is 1, then that will correspond to a box containing 8 ones, which will be w bar. Okay, and if I have 8 elements in the bottom 2, okay, then it will be w mere w. Okay, and if it is in the middle one, okay, these 8, if you are going to form one box, then w is changing, x is remaining 1 in that case. Okay, then it will become x. Okay, now one more possible combination is all the 4 ones in the top and all the 4 in the bottom are ones. Okay, in that case y and z is changing. We are talking about all 4 ones in the top row and all 4 ones in the bottom row. In that case, if you see here, x is 0 for the top row and the bottom row, then that will become x bar. Okay, so that is the way we make groups here. So this is one more example where you have all the 4 here. This is being club. So y z, this is giving x z. Okay, and this is going to y z. Okay, let me again. Okay, so it is just an extension of the 2 variable 3 variable thing, right? Okay. Now there is something, these terms we need to understand here, right? Because when we take up the QM method in the next class, these terms we are going to use again there. Okay. There is something known as a prime implicant of a function. Okay. Prime implicant means it is an yeah, first the implicant. Okay, first comes the implicant. Like if you have a function AB, ABC, BC, then each one of them is known as an implicant. Okay, so now for this particular function you have three implicants. So even the min term also can be called it as an this is a min term, right? So this is an min term. So this is an implicant. This is an implicant, this is an implicant. Implicant means for that particular combination, the output will be 1. Like AB is an implicant of the function. AB is an implicant means when A is equal to 1, B is equal to 1, F has to be 1. Okay, so this is known as the implicant. Okay, so for this particular functions, there are three implicants. Okay, now if you see, this is another problem in which there are four implicants. So 1, 2, 3, 4. So actually the function is not written out here. That function has got four implicants. So you have 4 ones coming in the truth table here, right? So there are 4 implicants, but you can group these into 3, right? Okay, so there are 3 ways you can group so the number of groupings are known as prime implicants. Okay, that means the total combination of squares which is possible here. Okay, it is shown in oval. I mean, we were talking in terms of square till now. So this is one particular combination of grouping. This is one particular. So there are 3 ways we can group these ones. Okay, now the all possible combinations will be known as prime implicants. Okay, what is this prime implicant? So the expression related to this round. Okay, so it is written 1, 2, 3, but there will be a expression corresponding to this, right? So those expressions, so those 3, they are known as the prime implicants. Okay, now if you see here, there is something known as essential implicant. Okay, essential implicant is like if you see there are 3 possible combinations, out of which this particular which is highlighted in bold, they cannot be done away with. Okay, because there is one here and there is only one way we can make a group here. So this becomes essential prime. Similarly, this one cannot be done away with. So this grouping has to be there. So these are known as the essential prime implicants. Whereas the third grouping, which is shown in dotted, this vertical one, that is non-essential grouping. Okay, because there are many ways that those ones can be covered. Okay, so that is known as non-essential. So what is essential implicants? Those groupings which cannot be done away with. That has to be there in the final expression. Okay, without this the final function cannot be realized. Okay, because this is one here, so that has to be somehow covered. Whereas for this one and this one, there are options available. Okay, so in this particular example, this third one is redundant. Redundant means even if you don't do that, still this can be. Okay, this function can be implemented. So this becomes an redundant. Okay, so this is known as a redundant one. So we'll see some examples, then it will become clear. So these are some of the terms which you should know, not necessarily for this particular class, but for the next class we are going to use these prime implicants and essential implicants in the next class. So let's take now one example out here. This is like we need to minimize this function in which the max terms have been given here. Okay, so all the max terms have been put 0, 0, this max 0, 0, 0. So now you have to club it. Now if you see here, this is known as the this 0, okay, and this 0, you make a square box. So if you see the one which is shown in red, okay, and here also you need to make one more box, and in blue you can make like this and you can make like this also. So there is an for this 0 there are 2 options available, like this and like this, whereas these red boxes there is no option. Okay, they have to be there. So these red groupings are known as essential prime implicants, and the expression corresponding to that will be, now these two will be like it is 0 0. If you see, this is become B is 0 into here, and C is 0 here, right? So it is actually B dash into C dash, or B plus C. In terms of OR gate, it becomes B plus C. Similarly, these two are 0. If these two are 0, how do we see? B is 1 out here, so it is B B C D, right? So if I have to write in terms of OR gates, I will write it as B dash C dash D dash. So you find this red, which is B plus C, and this red B dash plus C dash, they are known as the essential prime implicants, so they have to be there in the final expression. Now if you see, these two zeros, these have been covered. 1 0 is left out. Now 1 0, you can make either a blue box like this, vertical, or an horizontal. So they are known as non-essential prime implicants. So these are the two expressions corresponding to this blue line and this blue lines. Okay, so so the final answer could be this has to be there, the prime essential prime elements, and we don't have to use both of them. You can use one of them. Okay, is this clear to all of you? Sachin, is it okay? Yeah. Oh, okay. Okay. Now we take one more example here. Now if you see, don't cares in the truth table is given. These elements are don't care. Now if you see, since this is don't care, this is don't care. So this don't care, making it 1 is not really going to help us. But if we make this as 1, you can make, instead of an 2 excuse me, 2 ones out here, I can make a group of 4 ones, taking this as, so this don't care, I can assume it to be 1. I can assign a value 1 here. So this 1 1, this 1 1, this 4 becomes 1 box. Similarly, I have 1 1 here and 1 here. So if I put a 1 here, so these two ones and these two ones can be clubbed to make it as a bigger box. Now if you see here, by putting these two x's as 1, I can have just 2 boxes, 2 4 variable 4 element boxes, right? By putting this as 1 and this as 1, right? This I will put it as 0, because that is not going to make any difference to me. So I am going to put this as 1 and this as 1. So that simplifies my entire expression. Now if I take these two, if I say A is changing, B is not changing, so it is an B. And then and between this column and this column, D is 0, so it becomes an B D dash. Okay. Similarly, these two and this top 2, this bottom 2 and top 2, if you see there, so A is changing, B is 0, so it becomes B dash, and between these two, C remains 1, so it is B dash C. So I get the final expression as B dash C plus B dash. So so don't care conditions, if it is available, we can use it to our benefit to get a simplified expression. Okay, so thanks a lot. So with that, we come to an end of a 4 variable K map. But I would suggest you can go to my web page. There will be some more tutorials on digital design. I showed you that, right? So showed you the link, so you can go through that. You will have a few more problems, and you can also refer to your textbooks also. Even in the textbooks also, there are a few more problems. So you need to practice a few problems so that you get things right in your exam. Okay, thanks a lot. And